My name is Jill Slinger and I'm your course coordinator. I'm an Associate Professor at the Faculty of Technology, Policy and Management and the Faculty of Civil Engineering and Geosciences. I also hold an appointment as Visiting Professor at the Water Research Institute at Rhodes University in South Africa. In the previous knowledge clip on the governance aspects of building with nature, I focused on issues of scale. In this knowledge clip, I'll cover multi-actor systems and multifunctionality. But why do you need to understand these concepts? Well, using issues of scale, multi-actor systems and multifunctionality, you can connect your design choices to their real-world consequences. When these connections are made and are clear, decision makers, such as politicians, governmental authorities and field experts, can choose which design they'll implement. This is what you want as an engineer, that the decision makers can make informed choices about hydraulic engineering infrastructure and that they can understand how it will affect the natural and the human environment, how it will solve the problems. Now, in dealing with a particular problem, the people or the stakeholders involved can have very different perspectives. This holds for scientists as well as for the officials from local, regional and national authorities, and also for the public. When we discussed the issue of scale, you also learned that these perspectives can derive from their tasks, their work, or from their training, or even from their research field. More generally, in governance terms, we distinguish in our stakeholder analysis that stakeholders all have different perspectives. They all have a different view of the problem. We also distinguish their interests or goals. Each stakeholder wants to achieve something different. And what about their resources? Some stakeholders have a lot of money, and other stakeholders have a lot of knowledge or other resources. This results in differences in their degree of influence. Let me give you an example. A particular stakeholder is a member of the public living in a place affected by a planned building with nature intervention. He's a nature lover. That's his perspective. He favours interventions that will enhance the naturalness of the environment. That's his interest. But he's also interested in being protected from flooding and thereby being protected against loss of his property value. So that's another interest for him. However, as an ordinary citizen, he doesn't have specialist knowledge and he has few resources and little influence. Now, the situation is very different if the same citizen were a politician with great influence and a lot of knowledge of political processes, a person with influence and resources. This is just one example of an analysis of a stakeholder. When a number of carefully selected stakeholders are analysed in this way, an overview or a so-called stakeholder analysis of the diversity in perspectives, interests, resources and influences can be obtained. This can be used to identify groups of like-minded stakeholders or stakeholder groups with common interests, or even stakeholders who may block a process later if they're not included on time, the critical stakeholders. The groupings of stakeholders with particular features in common are called actors. And when there are multiple groupings of stakeholders, we have the actor part of a multi-actor system. But that's not all. The other component of a multi-actor system is the real world. And for us in this course, the real world is the natural environment and the infrastructural system in which those actors live. Once again, the concept of scale is relevant here. By this I mean not only the perception of scale of the actors, but the spatial, temporal scales and the level of aggregation that needs to be taken into account in order to be able to make a scientifically sound hydraulic engineering infrastructural design. If we draw a system diagram, we see this very clearly. If we zoom in, the degree of detail of the effects in the natural environment and the infrastructural world is high. We see more detail. If we zoom out, The degree of detail and the effects that we see is less. We have a helicopter view. We can see over a longer time period or over a larger area. So the system boundary, the edge of the box, determines what is taken as the problem space and what's taken as the context around a problem. This is usually called the level of aggregation. It determines what is seen as core to the problem and hence to your design. The selection of system boundary is a significant and influential one that often lies implicitly in the hands of the hydraulic engineer. It determines the spatial extent, the temporal variation, and the level of aggregation of the real-world component of the multi-actor system. But why is it relevant for you to use the multi-actor system concept? Well, it enables you, the engineer, to be explicit about 5 things. First, the boundaries of the existing natural and infrastructural system that are taken into account, the frame of the system diagram or the edges of the box. Second, the external factors or variations that will be considered. So when you design a flood defense system, this would include the frequency of occurrence of the floods to be used. Do I want it to withstand a 1 in a 100-year event or a 1 in a 10,000-year event? Third, the range of interventions and who's responsible for them or who can influence them. So which actors can do what? Fourth, the connections between effects within the natural and the infrastructural system. The engineer's understanding of how processes work in the natural and infrastructural system. This can be done with empirical relationships, or it could be done with advanced numerical modeling. Fifth and finally, the outcomes of these effects will be clear, and who's likely to benefit or not from the design. In summary, the multi-actor systems concept helps you to clarify how you choose to match actor requirements and real-world system requirements in your design. So that was multi-actor systems. Now we move on to multifunctionality. Multifunctionality is the concept that a hydraulic infrastructure can serve more than one goal simultaneously during its lifetime. But surely this is already addressed if you take the perspectives of multiple actors into account in your design. Don't you think so? Not necessarily. For instance, differences in the goals of actors could be so large that only 1 or 2 dominant actors whose interests align are well served by an infrastructural design. I'll give you the example of a moderately sized dam. It provides water storage, it's a component in an agricultural irrigation scheme, and it safeguards downstream areas against intermediate floods. It's a moderately sized dam, so the really big floods still move through the system and over the dam. Such a dam is multifunctional, but could still serve only the interests of a single actor. Maybe the elite or landowners with farming interests downstream of the dam. Many such dams were designed and constructed during the apartheid period in South Africa. So in this sense, the concept of designing for a multi-actor system is a broader concept than designing for multifunctionality, because you take into account the interests of multiple actors. Let's take another example, the Eastern Scheldt Barrier in the Netherlands. This barrier also serves a number of functions. It is a storm surge barrier, protecting the hinterland from flooding by closing when extreme water levels occur at sea. But it's more than a dike. It also allows for the exchange of water between the estuary and the sea, serving an ecological function of maintaining the character of the estuarine system. The continuity of sediment, water, nutrient and biological exchange processes is maintained. But it's also a cultural and tourist icon of Dutch water engineering. It's used for teaching Dutch school children about flood defense and about engineering, and it's a tourist attraction. When the barrier was designed and built in the late 80s, it embodied engineering for the ecosystem, taking ecology into account. It represented a paradigm shift at the time. Now, we no longer consider the Eastern Scheldt as the epitome of modern-day ecological engineering solutions. And I'll tell you why. There are negative consequences for the ecosystem. There are very steep mud banks and there's sand hunger in the Eastern Scheldt system. However, the Dutch have a new icon, the multifunctional sand engine, as a building with nature design in which multifunctionality was an explicit design requirement. So, if you take the diverse interests of multiple actors into account, you automatically come to a multifunctional design. But I think you'll understand that this can lead to a less efficient design. The more actors you have, the more functions you are required, and the less efficient it can become. And I haven't even mentioned the increase in costs. Another problem with multifunctionality is when the project brief is so narrow it doesn't allow you to design for multiple functions and multiple actors. For example, a new harbour that's only built for big ships and where the needs of the local fishing fleet are ignored. It is my sincere hope that via this course we'll be able to train up a new generation of hydraulic engineers with the theoretical tools, the integrated design competence to challenge and renegotiate such narrow functional requirements. Society needs engineers with the skills and practices to build with nature for a sustainable future. Thank you for your attention.